Hey, good afternoon, everyone. I hope you are having a great day. Let me introduce myself. I'm Gourav Yadav. I work as engineering manager in Intuit, lead API gateway in multiple platforms in Intuit. With me, I have Venkata. He's working as staff engineer, lead service mesh at Intuit. We are here to discuss about a critical topic of failover. We'll discuss how the services can stay resilient in case of disruption, how different strategies or solutions can help you, help the business to keep on growing without any customer impact, right? In past, we have seen like there are multiple outages have happened with multiple clouds. We all develop applications, thinking the outages are very rare, but when it happens, we don't have answers, right? So we'll try to address those answers and address those questions here and get the solutions at scale, right? I'm saying, yeah. Next few slides might be repetitive, or you know already about it with the previous session happened before lunch, right? Just for the interest of other audience, I'm saying I'll go through what is Intuit. Intuit is a global fintech company which helps customers simplify multiple financial decision making through tax and accounting products. Intuit is a lot of passionate about the open source contribution. We have made multiple contribution to Istio community via Admiral and Ergo. We are also end user for different products like Kubernetes and Istio. And that's where we keep on developing ourselves and more contributing towards the open source community. With that, I'll just talk about something more on the contribution part. We have Admiral as one of the major contribution we have done as a traffic team here. Admiral is a tool which is used for cross-cluster communication and service discovery. If you need more details, please reach out to the GitHub link and see more about that. In addition to this, we have Navik. Recently, we have open sourced this product. This is used for unification of configurations across different services deployed in service mesh. Please reach out, please see the GitHub link and provide your feedback, how is it, and maybe start doing more contributions so that we all can learn from here, right? In addition to this open source, I'm saying we have a beautiful, dev portal page. We are on a modern SaaS journey where we are helping developers so that we are abstracting a lot of things from the developers so that they can just focus on mainly on the business logic and don't worry about the the networking part or the the infrastructure part, right? And that's where the scale looks like this. I'm saying so we have more than 300 clusters running with having more than thousands of namespaces running with that, and more than 2,000 services running, microservices running, talking to each other, with thousands of developers, using this dev portal and the modern SaaS platform for their end-to-end, day-to-day work, right? I'll talk about the agenda now. So we have seen in the previous session we have talked about what is API gateway and mesh. We'll again just for the interest of other audience, we'll go quickly touch upon what is API gateway and service mesh, and then from there we'll talk about how the service is distributed and works in a distributed environment. And what are the challenges when some failure happens, in such environment, right? How we address those, the issues, at scale, not just the existing solutions. And from there, I'm saying we'll talk about what are the different solutions we can have for different use cases. We have explored a lot of different use cases, and we have found out what approach works for which use case. And we'll talk about those things in detail, right? And then we'll talk about the summary and the next steps for that, right? So what is API Gateway? It's one of the old platform in Intuit. I'm saying we have built over a lot of period of time. Think about as a developer, you're developing multiple APIs for a service. Initially you get a client, start accessing your services, all good, it works fine. The issue start happening when you start getting more of the different clients, right? You have mobile app, browser, different services within your service company, and multiple third party, right? And now the developer has to start focusing on the logic of authentication, authorization, right? Rate limiting. Let's say if one of the client does the DDoS attack, how would I, as a developer, can save my service, right? I have to think about those things and implement those part also, right? Now, if I can get a component which can do all those things, right? it would be good for me as a developer, right? And that's where the API gateway comes into picture, right? API gateway sits between your client and the server, your service, right? And provides you all that capabilities which we talked about: authentication, authorization, rate limiting, traffic dialing, and many more, and just gives you that flexibility for the developer that that you can just focus on your business logic, right? So as I said, in Intuit, we have built our own API gateway. We are not using the open source or any other enterprise version of any other API gateway. And this is how the stats look like in Intuit, right? I'm saying, so we have like 999, 5 nines availability throughout the year. We have seen 1.7 million TPS max TPS during the text peak. We have around close to 3 trillion transactions we do yearly, and these are for different, more than 2,500 services which are talking over API gateway, right? And the scale needs to be maintained, and with that, the capability has to be more refined and need to be optimized, and which we start doing, which we always do for that API gateway. Now let's look at another platform, service mesh. We have gateway in Intuit. We have also a service mesh. I'm saying, let's see what is service mesh. I'm saying in detail. So think about, we have different clusters. We have seen multiple clusters we need for our development. So here we have S1 as a service, which just wants to talk to S2, same cluster, and S3 in the different cluster, right? Now, if you want to have the same kind of capability, which is an API gateway, we would need similar kind of setup here also, right? So what will the option? I'm saying it will look like this, right? I'm saying, so it will be, the communication will happen, and over the API gateway, this request will go out of the cluster, and they'll go to the different VPC, and then again come back to the cluster, right? So you see there's a hop, right? But we want to avoid that hop. And that's why we need something, considering the Kubernetes world, right? We need something very close to the container or the pod, right? And that's why we need something called as like kind of mini gateway, which is attached to the pod. And that's where we are using Istio, which is another flavor of service mesh, which helps in doing a service-to-service communication, right? And that's what the service mesh is all about. I'm saying it helps in doing service-to-service communication in the most efficient way. And this is how the stats look in mesh adoption in Intuit, right? I'm saying, so we have again 5 nines capabilities, 5 nines availability in for mesh services. We have max TPS of 74K during the year. We have seen almost like 50 million yearly transaction, and these transactions are growing as the adoption is growing in Intuit. There are more than 300 clusters running and talking with the different services in these clusters, and that's how the scale starts growing, right? Now, since you now know the platform, what is gateway and mesh, think about how, as a developer, we think about how service works in a distributed environment, and let's now see the actual way where the issues are, right? So how we develop the services, right? I'm saying, so we have multiple regions, right? We have API gateway, we have a service, right? All the communication right now is happening via API gateways. Clients are communicating via API gateway to service. We have seen that service-to-service communication, if I want, I can do over mesh, right? All good, right? We have studied all this just now, that it was all possible, right? Now, see, what happens when the region goes, is this region sufficient for service, right? One region, right? In a distributed environment, you may not find it, right? Right? I'm saying, so you want that resiliency that, service should also be there in the other region also, right? So that's where we need a service, right? Now it looks, the distributed perfect distributed environment, right? So all good, right? Till now, right? Now, what happens on a fine day? You have an issue in that region, one region, right? Now, what to do? As a developer, what you're gonna first reaction is to, think about. Option one is let the platform team API gateway does the failover. Why I need to think about it, right? So API gateway team, if let's say take that decision and does the failover, right? What will happen? Think about it. I'm saying, right? That it will start failing over all the services which is onboarded to API gateway in other region. Okay. So coming back to that, the problem was that issue was in one region for our service, right? But with that, for that service, instead of that, we have done failover for all the services. So API gateway has done all the failovers, right? Now, does it really make sense that we are talking about an issue for a service, but the gateway is actually failing over all the services, right? So it seems like a concern here, and we'll come to this concern that we'll keep in mind that there is a concern with this failover strategy, right? What can we do? This was there in the API gateway part. Let's see, what we can do on the mesh side. So we have seen here service-to-service communication is happening from client to server over mesh. Now, what happens when the issue happens, right? When the region goes down, and the client is on mesh, right? So what you do is, as a developer, what you do is you just update something called as a destination, and in Istio we call it as virtual service. You just update the destination so that the client start calling the service in the other region, right? Simple, right? I'm saying it's just one client, you just updated it, and it all works fine, right? What happens when you have hundreds of those clients, right? I'm saying, so we have so many clients, right? What happens that way? As a developer, if I don't have any other option, I have to manually go update all those destinations. In Istio, it is all virtual services. We start updating those destinations, right? Seems like a very impractical job, right? I'm saying that's what I'm saying. It's very impractical to just update the destination with all hundreds of clients, right? That too during the disaster, right? I'm saying you are doing a manual work, right? I'm here, right? So again, we need some issue. There are issues here, and we need to solve those part, right? I'm saying so that's where we have seen now there are issues with the gateway, there are issues with the mesh failover, right? So let's come to a summary for problem statement, right? So we need a strategy, like a self-service strategy, which can help us, to failover those service endpoints without impacting the whole platform, right? Because if we are concerned only about one service, we don't want to impact other services. The customer or the developers for that other services may not want to know the failover for their services, right? So we need some self-service control, right? I'm saying failover solution. Next is there's a kind of lack of orchestration layer we need. We don't want to update the configurations automatically. We don't want to do manually. I'm saying we want automatic orchestration for those configurations. And that's where we need some solution like that, right? To serve, address those issues. Last but not the least, there are people who know about Istio. I'm saying you may know that there are existing out-of-the-box solutions provided by Istio, right? But those solutions may not be suitable for the scale which Intuit is working on, or any other services which are working at a high scale, right? And we'll try to address those use cases. Later, Venkata will talk about those use cases and how we can do the failover for those use cases at scale, right? With the improved solution, right? So with the problem statement in mind, I'm saying let's talk about solution now. So in Intuit, we have developed multiple DR solutions, from the traffic point of view. First we'll talk about self-service failover. So self-service failover, we want to give a control to the the developer, that how can you as a developer can have a control in the dev portal, that you can do, this is how the the UI looks like. The dev portal, every service owner, developer can just go to the dev portal in Intuit, and just see the topology for the gateway endpoints. We would see that there are multiple .com endpoints are given for a prod environment, and you can just see the topology for that, right? If you want to see multiple environments, you can just see multiple environments, and for that specifically, you can see the multiple endpoints for that. Now, if I have to do a failover, we can just edit the option for that endpoint and do the failover for those, right? This is the capability we have built in Intuit, and giving that a developer that ease, so that they don't need to worry about all those things in a regular day-to-day basis, and they can just simply come to the portal and do this thing. This is how it looks like on the gateway perspective. What about mesh, right? So on the mesh, we have .mesh endpoints, right? And this is how it looks like the UI. We have multiple mesh endpoints. We show the topology for those endpoints, how it is correctly configured. Is it active, passive, or active, right? And what is the status of it, whether it's updated or not, right? For those, once we have those status, right? We have again, you can have edit options, which we can edit it and make the topology of that .mesh endpoint, specific endpoint. You can change the topology, right, and make it as as what you want. You want to move it to some other region, you can have it based on the active passive, based on option, right, and submit it, right. And the feedback comes back, and just your service is failed over with that for that endpoint, right. Right. This is how the simple we have made it for the developers, and that's the experience we have given to the developers. Let's see, we see UI, right? I think for the people who want to know what is underneath it is going on, right? For those, let's see this architecture, right? So how that happens is a request comes from the client, and it goes through the Intuit API gateway. Now we have seen that Intuit API gateway, what it does is it does all the authentication, authorization, rate limiting, and make sure that the request is genuine. It should not happen that I am doing a failover for a service which is I'm not the owner of, right? So it should take care of those things, right? So that's how it happens. After that, service goes to a DNS manager. A DNS manager is also another service, a Lambda service, which we have developed in Intuit, which does all the capability of managing the DNS of the services, right, of the .com endpoints, right. What it does is it's actually helpful. It talks to Route 53, and makes that all those calls to the Route 53 APIs and make the changes of the DNS. And once the changes are done, the feedback is given to the user that the failover is completed for that for your endpoints, right. The Lambda service, the DNS services, is responsible for the DNS management of both gateway and mesh, and we'll see how the mesh happens, right? I'm saying it is behind the AWS API gateway. Since it is a Lambda, so it is also needs to be backed up by the AWS API gateway, and that's how it is working. I'm saying, so yeah. This is how the experience looks like. Backend experience looks like for the API gateway endpoint failure. Let's talk about what is the mesh endpoint failure happens, right? Again, same setup. Request comes from the developer. It goes through multiple gateways. It comes to DNS manager. Now, after the DNS manager, what it does is, obviously, the gateway endpoint was more of .com endpoint, so it was talking to Route 53. Now, in case of mesh endpoints, what we do is we send a message to the Kafka. The message is with all the attributes which you want to fail over, right? The endpoints, topology, all that, right? And now, our open source contribution, right? I'm saying open source component Admiral comes into the picture and takes up all that messages, consumes the messages, and does the try to update the configurations for those different clients, right? Then that's where the update happens. So the Admiral is there responsible for updating all those configurations at scale without any manual intervention, right? It is doing updating the destinations, again, virtual service in Istio, which is getting updated here, and that's where the one endpoint is getting failover into the other endpoint, other region, right? I'll invite Venkata to talk about the other strategies about automatic failover. Both the strategies are required. We need self-service, we need automatic. We have seen there are different use cases for it, and we also need automatic also. So we'll talk about those things, and Venkata will take over that.
Okay. Yeah. Hello. Yeah. Thank you, Gourav. So let me recap what we have seen so far. So what we have seen is a set of orchestrators built, and they are backed by a nice UI using which developers can easily log into their dev portal UI, and they can choose on demand if they want to fail over a particular service. They go to a particular endpoint and simply do an on-demand failover of a particular service. So this strategy is needed, and this requires a manual intervention. So what about automatic failover? So when I say automatic failover, without any human intervention, if you find a service is degraded in a region, so the clients should be able to move their traffic to the appropriate working region automatically. So how do we do that? Let us see what strategies are there. So to ensure that your service is automatically moving to the other region, so you need to have well-built health checks. So let us see what the health check mechanisms that we have seen today in the famous platforms. So one of the health check is passive health check. Okay. So we'll talk about each of them in detail, and we'll also see where they work well and where they don't. And another one is active health check. So most of the platforms like Istio, they give these health checks, and these algorithms are available to you on day 0, and you can configure any of them. So in addition to that, I'm going to introduce another health check that we have built at Intuit, and I'll also mention the reason why we have done that. Let's see each one of those health checks. So the first one is passive health check. So this is also known as outlier detection in Istio. So what is passive health check? So in passive health check, the client sends request to a service, and when the service responds, it uses the status of the response to identify the health of a service. So an example, a client sends all HTTP requests to a service. If the result codes are 200 OK, yeah, it deems that the service is healthy. Whereas if it receives 5xx or any other error codes that it is configured, so it considers that the service is unhealthy. So let's say you have a service in 2 regions, so region 1 and region 2. And then you have a client, right? So you have a client cluster, and it has some set of pods. Let's say I have configured here this service, this client, to ensure that it always talks to service in region 1, which means the service is working in active-passive mode. So at this stage, all the client pods in the client cluster would trigger requests only to the service in region 1, right? Now, I configure a passive health check. So a typical passive health check configuration would look something like this. So in a sense, what it is trying to say is, check every 15 seconds. If you see 5 consecutive 5xx in the last 60 seconds, then fail over to the other region for 5 minutes. So with this kind of a config, so let's see what happens. Since you apply the config and it's a distributed environment, you see that it gets distributed to all the client pods. So when we say client here, there are multiple client pods which are actually triggering the requests. And all these client pods would have got this passive health check configuration that we have given. Now, let's say one of the client pod has received 5xx from the service. So we do not know from which pods, but the client, as it sees when it sends a request to the service, it has received 5xx, and they are matching the configured thresholds of the passive health check configuration, right? So at this stage, what it do? So according to the config, so the client moves to the other region, and the traffic is moving to service in region 2, right? But it is possible that not all pods in your client cluster would see the same effect. So some client pods would have not hit that particular threshold of 5xx error codes that you have configured, and they continue to send requests to that service. And eventually, when those client pods also see that the service has failed because they have hit the configured threshold, they too will move the traffic to the other region. So this is what we call as passive health check. Now, so let's see in what all cases does it work fine. So it works fine when there are smaller number of pods in both client and service. Also, this works very well, and it allows you to recover from temporary service disruptions. So we'll talk about why only temporary service disruptions a minute later. Now, let's see the other health check, which is called as active health check. So as the name indicates, so here in active health check, the clients would trigger health probes to the service and expect the service to respond back. So depending upon that, they consider whether the service is healthy or not. So which means, once again, you have a service in both the regions. And let's say I have a client in client cluster 1. So let's say I configured this in the load shared mode, which means the client is configured, the service is configured in load shared mode, and the client is free to send requests to the service in both the regions. So at this stage, if I configure an active health check, the configuration would look something like this. So you can relate this configuration to one of the Kubernetes probes, like liveness probe or readiness probe. So effectively, it says, every 1 second, send requests to /health path of the service. And if you don't receive successful responses for 3 consecutive times, consider that the service is unhealthy. So this is what a typical active health check configuration would look like. So with such a configuration in place, once again, since we are in a distributed world, this configuration applies, and sits in all the client pods, right? So all the client pods are exchanging these health probes. Remember, these health probes are in addition to the actual payloads that the client is supposed to exchange with the service. So this is an additional overhead. So let's say at some point in time, service 1 degrades in region 1. So during this time, both these client pods would eventually fail their configured active health check configs and would ignore those failed endpoints from active routing list. So essentially, the entire traffic would be flowing to the region 2. Now, we have seen 2 different types of health checks, so which are mostly bundled by most of the platforms. And just like passive health check, even active health check also, it works well when the number of pods are small, both in client as well as service. Now let's try to see the limitations of these health checks. Now, we are going back to passive health check. So as we have seen, passive health checks experiments the service health with the actual payload that it is supposed to send and serve, right? So which means you send a request, the actual request. Only when the service responds, you will get to know whether it was served properly or not. So this is one limitation of passive health check. So I have also mentioned that the passive health check works well for temporary disruptions. The reason is most of the passive health check algorithms that you have today, okay? So they come back to the original region once the ejection interval is over. So if you remember in the passive health check config, there is a parameter called ejection time, so which is configured to some minutes, some 5 minutes in our example, which means the client moves the traffic from service in region 1 to region 2, and after 5 minutes it comes back, which means the understanding is that after 5 minutes the service is in region 1 is going to come up and alive, which may not be true always. The service has a prolonged issue, or if the region is down, then you are bound to see the same failures again, and the client is supposed to undergo that entire exercise of identifying whether the service is healthy or not using this passive health check mechanism. Now, the service health visibility may not be uniform. So this is very evident when you have large number of pods in both client and service. Let's say you are running thousands of pods in client cluster, and you are running thousands of pods in service cluster. So let's say at T0, one of the pod in the client identified that the service is down, which means it has understood that it has hit the configured threshold of passive health check of consecutive 5xx within a particular time, right? And if there are thousands of pods, if you consider the time at which the last pod in the client cluster has moved the traffic, so the time gap between the first pod versus the last pod, it could be huge. So when someone asks, what is your time to detect and what is your time to failover? So the time could be very big in this case. So the effect of this is slow detection and failover. So long as you have larger number of pods in client and service clusters, so you might take larger amount of time to failover your entire client cluster from one region to another region. And then coming to active health checks, as we have seen, active health checks would trigger additional traffic volume, which is the health check volume, in addition to the payloads that they serve, right? So imagine client and service having thousands of pods, and if you enable active health check, so you're actually overloading the network by that much, right? So these are some of the limitations that they are present with the existing solutions. Now, let's see you have a mission critical service, and which operates at scale, which means the service has thousands of pods, and it connects to thousands of clients. And let's say clients also have very large number of pods. Both these solutions may not give an optimal result, right, in terms of SLA, in terms of failover, service disruptions, for such a case, right? So that's the reason why we have built a new solution. So let me call it external health check solution or external health check service. So let's see what it does. Primarily, it attempts to offload the health check from the actual client pods to a dedicated set of pods, which means I built my own system, which is capable of doing the health check. So for doing the health check of the system, I can employ various techniques. So one of the techniques could be the one that is used by the active health check itself. And then this external health check service is capable of monitoring a dedicated set of services that is configured to, which are really mission critical, which do not want to employ the solutions that are provided by the platforms by default. But it does not end there. So the external health check service is also capable of communicating to some of the orchestrators that we have seen before. So let's see the advantage of it. Let's say this external health check solution identifies that the service in so-and-so cluster and so-and-so region is down. Then it can output the same health check status to some of the controllers that we have built. Let's say it outputs it to our traffic controller, which is Admiral. So Admiral is a traffic configuration modification controller, which means it can alter the traffic routing between different clients and services on service mesh. So when Admiral sees such a status, okay, then it can possibly take a decision whether to change the traffic pattern or not, right? So similarly, let's say I have also built something called a resource controller. Okay, it could be a Kubernetes resource controller. And when that controller gets the health status, so then you have a chance there to ensure that you take some actions like resource config changes. So we'll see how we can put this newly built solution, external health check service, into action for such a mission critical service, which is operating at very high scale. Yeah, so the health check controller is ready, health check service is ready, and it is ready to output the health check status to all the controllers that we have seen. Okay, and then we have a service which is available in both the regions, and we have a client which is ready to send requests to all the services in either of the regions. So let's say I configure this service in active mode, in the load shared mode, which means I say that the service is ready to take half of the traffic in region 1 and half in region 2. And then I also configured our external health check service to monitor this particular service, service 1, right? So at this stage, the external health check service is monitoring the service 1, and as we discussed, it is capable of outputting the health status to all the controllers that we have built in. So what happens? Let's say this information goes to Admiral about the health status of a service. Then Admiral says, oh, the service is configured in active mode, and it is in load shared mode. And Admiral also is aware of all the clients and where they are sitting in. So the Admiral is all aware, so it knows. And it configures that particular client, all the clients of this particular service, with the appropriate traffic topology, which is 50% to one region and 50% to the other. So let's say this is how the requests will go once the traffic topology is made 50-50. So at some point in time, a service is degraded in region 1, right? So what would happen? At this stage, the external health check controller would immediately trigger notifications to all the, the orchestrators available. So once it goes to a resource controller, then resource controller here has an opportunity to give some commands to the service in region 1 so as to scale up from the existing number of pods to a higher number of pods in anticipation of the traffic failover. So in this example, I've indicated the pod scale up alone, but however, it is not limited to that. So it could be scaling up of your ingress or even scaling up of your database, right? It all depends upon the use case. But you have a way to do it, and you have a plugin that you can attach, and then you can ensure that all those things are done as and when the service is degraded in one region. So similarly, external health check controller, it would have also sent the same request to Admiral, and Admiral identifies that the service is down in one of the regions, and it would immediately change the traffic topology to the other region. So, and then thus, the client would stop sending requests to the service in region 1, and the entire request flow to region 2. So this is the solution, and we have seen total 3 health checks, 2 which come out of the box to on many platforms like Istio, passive health check and active health check, and the one that works well when your services and clients are operating at scale, which is what we have built at Intuit. So let me sum it up. So to stay ahead of disruptions, ensure that you have orchestrators in place, so which are capable of understanding the request that the user gives, either via dev portal or whatever, and they can quickly alter the traffic topology across all the clients available. And then ensure that you have chosen proper health check mechanism. So it could be an active health check or a passive health check, or sometimes a combination of both. Or if your service is mission critical and if it operates at scale, then you can choose to build a dedicated health check service that we have shown here. So it all depends upon the use case. And then also have self-service available. So it's not sufficient if you have orchestrators built in. So there should be an easy way the human can communicate to those orchestrators, preferably backed by a UI, so that the traffic change on demand can happen smoothly. Last but not least, so it's always not about failover. You should also consider pre-scaling the resources, and this can easily happen when you build a standalone solution that we have just shown here. So it may not happen with the built-in solutions that you see with some of the platforms. I think that's all we had to present. Thank you, and we are open for questions.
Any questions, something, please?
Yeah.
Mic, can you come to mic? In between, I'm saying there's a mic.
So where is Admiral hosted? Is it on Kubernetes cluster or it's sitting outside?
Admiral is hosted in our a special cluster called PaaS cluster. So
Okay.
it's a Kubernetes cluster, yeah. It's another Kubernetes cluster.
What if the Admiral cluster goes down?
Yeah, so we have a DR for Admiral as well. We have a disaster recovery for Admiral as well.
So who is managing that DR automation for Admiral itself?
Yeah, so the DR for Admiral is managed between the two admirals or the admirals running in both the regions themselves. So it is not using any of these techniques.
So will it not create a split brain issue or something?
So we use a health checker kind of a solution using a database. You write a key to a database and then you determine which of your admirals want to be active and doing the job.
Okay.
So it's that kind of a solution. It's not based on
Health check.
Health check that we have shown here.
Okay, and in one of the slides you had like Admiral will be reading it from Kafka and then it will be pushing it to all.
Yeah.
So in one of the previous session, they were discussing like something similar. At that time, they were using S3 bucket, and all the pods will be connecting to S3 bucket to update the config. Why can't we use Admiral there as well?
S3 bucket to connect.
I think-
No, okay, Admiral.
That is for the
Yeah, I'll
traffic,
tell you.
traffic
For the
thing, basically.
configurations,
I'll
right?
tell you. So Admiral is a service mesh config orchestrator. It only knows and understands to translate the input to the corresponding service mesh configs,
Okay.
which is only Istio specific.
Got it.
Yeah.
Sure, thanks.
Hello, I have another question. So first and foremost, thank you for the informative session. And second is regarding the external traffic kind of auditor, which you have mentioned about. So basically, internal and active and passive are fine. Although regarding the load which you mentioned, right, that if we make, let's say there are thousands of clients and thousands of servers, there's a direct health check request which goes, and it creates a lot of pressure on the services, right? How are we preventing that with an use of an external health check provider? I mean, like, it also makes a request, right?
Certainly, I think you cannot go away with health check probes. The only thing that we are avoiding is we are offloading clients from doing these health checks. Okay, and if the clients are scaled up to a larger number, which is not the case with our dedicated infrastructure, there you have a limited set of pods which would do the health check, and you do not load the system to that extent.
That extent, right?
It is the volume which is mattering here.
It's a scale.
Few health checks will not have an issue for our services. The only about the thousands of pods which are having doing the health check at that volume. So that's the I would say the issue we are trying to avoid.
And how are we hosting that health check mechanism? I mean, like, is there any automated service, or like how are these health checks happening? Is there a cron or like Lambda, or what's the compute or logic behind that?
So health checks service also consists of pods which are capable of understanding different health check mechanism, just like the Kubernetes allows you to do procs using the TCP, HTTP. So we have a similar variant.
Because there could be a combination of gRPC or
Yeah,
HTTP.
certainly, yeah.
Okay.
Hello. So my question is, you mentioned that you developed the external health check just to offload some of the, the job which is being done internally, and you offload that.
Yeah.
So can it be possible with the sidecar containers?
Where? Sidecars where? On the client side?
In the service mesh? Like sidecar can be integrated with the Istio?
No, yeah. Okay.
So I was asking that if the sidecar can do that job.
No, it is the sidecar doing the job, but what we are doing, even if the sidecar does the job, it is triggering large traffic volumes when the clients and services are scaled up to higher numbers. So we have a couple of mission critical services at Intuit, okay, to which most of the other services at Intuit are clients. So in that case, imagine 100 clients, each having, say, some 500 pods, talking to this particular service. And everybody is doing health check because everybody wants to talk to that particular service. At any point in time, it is mission critical, right?
Right.
So these many services, either the client application containers or the sidecars attached to those client pods, they would overload the traffic once again, right? The network between these clients and services, right? Which is not needed.
So anything which is coming from a pod, right? So a sidecar is also part of the pod only as a container, right? So,
Yes, right.
So the if you have thousands of pods, you have thousands of sidecar.
Yes.
It's just like them. So the volume remains the same, right? I'm saying it doesn't changes. And that's what we are trying to avoid, I'm saying, by
So
not
it's
having.
not offloading the job of an application logic or application container. It's actually offloading the client cluster itself, the client service itself completely from doing this job.
Okay, okay. And is this API gateway publicly available? We
No.
can use, no? So it's internally developed, only internally for use. Okay.
You
Thank
can use Admiral and Navic.
No
Okay,
worries,
thank you.
Hey, I have a quick question. So you have 300 clusters, more than 300 clusters on board to this, and you also said you have more than 2,000 services, right? More than 2,000 services. With this ambient mode now is G8. I wonder what's your plan? Are you seeing this? You're going to adopt this? Or are you going to have like a migration plan, something like that? Just curious.
So-
Thanks.
Yeah, I think we have experimented with ambient mode, and there are plans to adopt ambient mode. But even to roll it out, right, at an Intuit level, I think we need to do and prove with a lot of performance testing. And the major challenge is at Intuit what we face is we have extended Envoy with our own custom filters.
Yes.
Right? So we need to check how ambient works with Envoy filters. So we have a lot of Envoy filters at both client side as well as service side. So we need to see if all those things work fine or not. So that's the major task. Okay. We are certainly on it.
Okay, thank you.
Thanks.
Right. Thanks for the nice talk. So one question around the auto-scaling piece. The implementation sounds like KEDA, like where KEDA registered itself as a external metric server. So the health check thing, does it operate like that, or it is completely external to Kubernetes?
No, I think it is within Kubernetes, because at the end of the day, if a service is on service mesh, okay,
Right.
so you need to be in Kubernetes even to send some probes and estimate the.
And to auto-scale, like, are you feeding some data to HPA? Like, how
Yeah,
does it?
I think similar to that, we have some custom solutions built around
Okay.
HPA. Yeah.
Thank you.
Okay. I think we are good.
Yeah.
Thank you, everyone. Yeah.
Thank you all. Have a good.